Hello and welcome to El Zoominario. Today we're very happy to have Marcela Tabima Martinez. Marcela first started to study pulmonary hypertension after she was awarded the Fulbright scholarship in conjunction with Colombian government to join the vascular tissue biomechanics laboratory housed in the Department of Biomedical Engineering at the University of Wisconsin-Madison under the supervision of Dr. Naomi Schesler. Upon completion of her doctoral studies, she joined the Vascular Medicine Institute at the University of Pittsburgh under the supervision of Dr. Mark Gladwin. She came back to Colombia to join the Biomedical Engineering Department at Universidad de los Andes as an assistant professor for 3 years, and she's currently an associate scientist at the University of Wisconsin-Madison. Thank you very much, Marcela. We're very happy to have you, and please get started whenever you're ready.
Hello, everybody. Like I was saying before, I am my kids brought something to home, but like I am trying that my voice is with you all the time. For me, it's a pleasure to be here. I was reading the instructions of what we need to do, and I was looking the previous one, and I was like, I'm reading like the thing that I say about who I am, and I realized it like looks like pieces and things. So I decided that the first thing that I'm going to show you is like a little of how releases like looks like that they are completely disconnected, like in a moment connect, like the same than research. And like you think that is going to be a straight path, and like here is the path, but like you start to see branches everywhere. So it's part of the thing that I want to share today with you. I put my timer to be sure that I don't go long. So here is like the path of my life. It looks like can be, if we look at really, it has more branches, but like we're going to say that it's only some curves, only that. I am from Colombia. I am from Bogota. And I did my bachelor in chemical engineering at the University of Los Andes in Bogota. And like when I was finishing, was like the department was really focused on polymers. And I was like, polymers is something really nice, but it's not something that is like my passion. And at that moment, one of the professors in mechanical engineering, and like all of us were in the School of Engineering, we were able to be together. He said like he was working in cardiovascular biomechanics. And I said, this is really cool. But he said, okay, you are a chemical engineer. I just came from a tissue engineering symposium, and they were talking about this material, this magical material that can be really good for regenerative medicine. And I was like, all this word called like my attention, like, ooh, what is this? So regenerative medicine, I said, I don't have a clue, but sounds nice. So I start to read about that, and I start to look like for the guy that he mentioned, Dr. Stephen Badilak, that he's in Pittsburgh. And like I start to read, and like the material that is like magic is like from the swine, it's porcine, and it's from the intestine. So I start to read the protocol, try to do the things, and I was like, I don't get it. We don't have all the material. So I was like, okay, I'm going to send an email to this guy. And like for my surprise was like this big guy answered, and he sent me his protocol, and like I start to modify his protocol, and we go back and forth. So for me it was like, here from Colombia, I am able to talk with this guy, and he's giving me advice. And like I have another professor in Colombia that was helping me to change like the solutions and everything. And like finally we have a protocol that worked and was consistent. That was during my bachelor. So we were super pleased because it was like we were copying something, we were developing with the thing that we have in Colombia. And like we talked with a dentist, and he said, this looks super nice. I start to put cells, I grow like really happy. So I start to have like some in vivo studies too. So I was like, woohoo. So I started to do my master in mechanical engineering over there by following this path. And was really nice because it's like, was the three of us, and like two engineers and a dentist. And like the thing started to be super promising. So we were able, but we don't know anything about regulation or anything, but we start to learn, do tests, and like we do canine. That was the model that we used over there, and was super promising. So we start to do like the process for FDA in Colombia, and we were able to go to patients and everything. That was more than my master was. I was like a professor over there for 3 years too. So it was really nice because like an idea that come from an idea, we start to do it. And like it was a company that we started the company in 2000, and it's still there. So I was like, woohoo. But like, so I was at the university and I really like to teach and I was doing all the tissue engineering. And like I said, okay, if I like this one, I need to learn more about research. And I came here to visit a friend and I met the one that was my professor, that is Dr. Naomi Chesler, and she was working in biomechanics, of the vascular, like in the right side of the heart. So I was like, the heart is an organ that really calls my attention. So I was like, okay, this sounds super cool. What are you doing? And she said, like, I am trying to put these animals that they have the disease, and like we study like through mechanics what happened to the vessels and what happened to the heart. So I said, this sounds good. And she said to me, I don't have any money. So if you want to come, you need to find the funding. So I went to Colombia, I applied to the Fulbright, I got the Fulbright. So it was like that thing, like you feel like you can, but like, okay, it's the path for me. So I did it. And like we start to study together these things. And so she's a mechanical engineer, sorry, and I am a chemical engineer. So we were trying to, okay, how we're going to put these things together. And like, this is back in the 90s. So she always had the idea, because like both of us are engineers, to try to understand like the heart and like the arteries, like tubes and a pump. So that was our approach. So we started like, okay, we're going to take one of the arteries, and this one is like this one, like the main PA. And like we were studying what happened outside. And like we are engineers, we try to put like the stimuli is going to be mechanical. So what's the pressure and flow, and see how that changed. And we start to study these blue ones were the endothelial cells that you are going to see that happen, come in my future later. And like we were trying to stimulate them and to see what happened and change the pressures and see what happened with the whole vessel. And we start to understand what was happening there. And after that, we say, this is an organ, this is a part of the organ, but we really need to see what happened with the whole vasculature. And like I said, the thing that we were, and maybe I didn't say this, but like the thing that we try to see is what happened when you have a elevated pressure. That is the same that happened with your systemic body. When you hear that someone has hypertension, it's like your pressure goes up. The same happened with the lungs, but like if you see, everything is shorter. So what like it was fascinating, because it's like it's the same cardiac output. It's the same volume around the body. It's the same that go to the lungs, but like the pressures are different, the vessels are different. So it was fascinating to see how really all that blood was changing what happened in the lungs. And like the way that we studied this one was in the time domain and the frequency domain, like say like engineers thinking like we have capacitors and see that we have different tubes that are together, what happened and what happened with the current or the flow. So it was really nice, because we start to understand how change all the different like branches, how they were having changes. But like finally, this is a disease that is not that common, but like it's really bad when affect the heart. So we decide, okay, finally we are going to study what happened together. And we start to look how is that that coupling between heart and lungs. And like at that moment was not that many catheters like to study that part. So we were one of the first ones that started to use the catheter that measure pressure and flow in the heart of a mice that goes to 600 beats per minute. So that was a big thing, and we were able to do it. And like we learned a lot of how was changing with the disease, how really you have compliance changing in all the vasculature, and how the waveform that comes back is different. So it was really nice. And like I was saying, okay, I really like to see how a mechanical stimulus can change what happened with the cells and the physiology. But it was a lot of biology that I really don't understand. So I decided, okay, it's time to learn a little bit more about this one. So we went, after my PhD, I went to Pittsburgh to learn a little bit of what happened, like the molecular biology behind. And I found this guy, Mark Gladwin, that is a big person looking nitric oxide, what are the effects that happen in different diseases. And one of the diseases that he was studying was pulmonary hypertension. So it was really nice, because he's an MD, so has like a different way, like, okay, really, we really need to be looking for the patients, and like this has to be like something that is going to affect a patient. So I like that, like that way to think about a problem. So he was looking for therapies, and we did preliminary studies in the no, like therapy, and like after that was a couple of patents that like really how show a lot before me, and after that some like really how the effect of nitric oxide in these things. So after it was a short postdoc, but we were looking, and I have here, I was really interested in the relation between the cardiovascular diseases and diabetes, because if you see something is the thing that now the people call like metabolic syndrome, that you have like combination of the both, and it's two triggers that really can have troubles for your heart. So we start to do like animal models for this one, and it was short, but they continue, and it's a huge area of research over there. So part of the thing that I want to show is like things that you live can continue not with yourself, and then after that is going to bring you, is going to come to your life again. So I'm going to show you how. So after that, I come back to Colombia, and like at this moment, the one that was my advisor, two more guys came back from doing their PhD in biomedical engineering. So the university said it's time to start the program. So I was one of the four first professors to start the department. So that was a big thing, because was like we were going to start to put together what was going to be the curriculum. When I arrived, they were more, I was, or they have already big part of the curriculum. And like I was working before in Colombia, and everything that was tissue engineering, that was like my baby. So I was like, okay, I didn't train about that one, my PhD, but I did it before. So I started with a really nice group of undergrads that were super enthusiastic, super smart. And like one person that when I left, my advisor trained more people. One of the ones was trying to do sponges from the one that we have chips. And like they didn't have any success. So we start to think about like, okay, here is like where my chemical engineering can come. And we start to look, and was really nice because we were able to do sponges. Took us a while, but like, and like the thing that I said, I am here now, but the story about this one is like, at this moment, I talk with the student that continue and that finish a PhD and everything. And like, at this moment, they have the first patient that has sponges now. So it's like, it's really nice to see like, okay, it's like, it's a group of people that is doing things, and like you have like a little piece of the work, and like everyone, all the group can move forward. So that was really nice. After that, we did another patent for one of the products that we started with the dentist before. So that was for a scaffold that have titanium, and in that case was for bone regeneration. That was really nice. And another group of students were like, we really want to do, because we were working with a lot of bone people, so they want to do like adhesive. And like I say, like I don't have a clue about adhesive, but we can learn about adhesives. And like, it was really nice because we were able to have some proposals internal from Colombia, and like some help from orthopedists and everyone. So it was really nice. We were able to have 2 grants, and like we graduated like 4 students doing this project. And it's really nice because 2 of them continue and did their PhD in France in this topic. So, and he's now working in a big company doing that. So it's really nice to see that. But like, life, like I say, is not, so you were saying I will continue, but life have another idea for me. So we came back to the States. And when I say we, is with my husband. So we came back here to the States. And like I said, okay, what is next for me? So my husband found a job here in Madison. So I say, okay, I'm going to contact my advisor to see what she's doing and if she has room for me. And she said, it's perfect. I am leaving. I'm going to go to sabbatical. I have A, B, C, D, F idea. And like, maybe you can do it. So what is F idea? F idea, I put this one because I worked with her like for 4 years, and we were doing like it's a big parenthesis, the one that I'm going to do, like the disease that I mentioned to you, pulmonary hypertension, has a big component in hormones. So it's like you see more women that can have the disease, but like the outcomes are better in women than guys. So we decided it's something that we really need to study. So that was one of the things that I was doing. But the other thing is about the scales. So with the thing that I learned a little bit with the No and Ross, so we thought about mitochondria. So that was part of the thing that I started to do back in 2015 here with Naomi. And the other thing was like, she said to me, Dr. Thompson, really want to do engineering a small diameter vascular graft. And she said, and I don't have a clue about this one, but I know that you have some ideas about this. So I say, this is going to be the one that I can be able to put a lot of the things that I have done in life together. So I'm going to, so why a graft? Like, you know, cardiovascular diseases is one of the big things about worldwide. We have a lot of issues with cardiovascular diseases. And in general, when you have a cardiovascular disease, you are going to have arteries that are going to occlude or that you need to replace. And like at this moment, the gold standard are your own vessels. And like the best vessel that you can have is your own vessel. But the problem is like if it's an artery, it's really difficult because it's deep. And like I said to you, it's people that has a disease, so it means that it's not available. And like the one that the people really use is veins. But the veins, the mechanical properties of veins is really different. And they can have some issues. Like for example, they can form thrombos, they can have aneurysms, and they can have neointimal hyplasia. That means that after a while, they are going to occlude. So the thing that some people are looking is like synthetic vascular graft. And like when you have big vessels, I say big vessels is a diameter bigger than 6 millimeters, EPTF and that can work super well. But when you go to little diameter, for example, the ones here in the heart, they start to fail. For example, only this one. After 5 years, a vein is 74% and a heart is 39%. So that was the project that Dr. Thompson wants to do. He's one of the persons that works a lot in IPS and inducible pluripotent stem cells. So he decided if we use these cells in a really good material, we can have these grafts. So we start like the group, think and put the proposal together about what is the thing that we need. So we need some material that is compatible. That means that you don't have thrombus and that the immune system is not going to have any response or a minimum response that have the appropriate mechanical properties. So like the compliance and the strength is the one that you need. And like the properties, physiological properties are good. So it responds to a stimuli, neural or chemical stimuli. And finally, like we want to engineer an artery, it has to be able to, you need to be able to do it. And like it has to be cost, benefit, efficient. So thinking about a lot of the things that was already done and like has been proved that can work is like if you have a good endothelium cell. So that was like I said, like at the beginning was one of the first things that I was trying to stimulate. So here is like if they are aligned and they are metabolic active, they really can help to avoid some of the thrombogenic effects and everything. So that was the thing that we decided. So we decided like we have the IPS that we can induce and like we can differentiate in order that they are arterial endothelial cells. And like we have material like the EPTFE, if we try to put it in small diameters and have these cells and we have the right stimuli, is going to be an artificial artery, a small artificial artery. So I start to say, okay, what are the requirements that we have? And like, if we think about an artery, it's like here is our endothelial cells. You have the stimuli that is the flow and the thing that the cell is going to sense, that is the shear stress. The same happen with the pressure and the thing that the cells is going to sense is the wall stress or the strain of the changes in the wall. And finally, in the longitudinal direction is the strain too. So we say, okay, all of these are important. They act independently and at the same time in the cells and modulate what happened in your artery. So we say, okay, the first thing like we decide that is endothelial cell, the first thing that they are going to sense is the shear stress, is the flow. So say, okay, we are ready to put these cells. We're going to put these cells, these very nice cells, and we're going to try to have, and that was the part that I need to do, a bioreactor in order that we can characterize what happened. So we start to design different things. Like we say, okay, that I am able to see the cells, that I am able to mature the cells there. After that, we were thinking it has to be something long in order that we have a bypass, we're able to do it. And we need to be able to have 2 stimuli. And like I did iterations of all of these things. And like we try to modulate what was the physiological waveform. And like we create physiological waveform, have feedback to be sure that the bioreactor can have everything. And we say, we are ready to go. So we're going to put it here. this is one of the first one that we put, like we have different conditions, but we thought that we were in the optimal, so we put it here, and we compared with one that was clinical proof, like is fibrin glue. So we compare, and like static, they look beautiful, and after 2 days in flow, we didn't see anything. So we were like, okay, we need to come back and see what are the variables that we really need to have. So, and these are 4 of a lot of more variables that you need to have in consideration. But like first is the EPTF feeder material. So this is a material that is really hydrophobic. That means like nothing attached to that. So we do changes to that one in order that the cells attach. The other one is, like I said, like you need to do something to attach. That is the coding. I think that I need to move a little faster, so I'm going to start to move faster. So like in order that you change that properties and the cells feels okay. The cells, because I haven't mentioned anything of this, but like we want that the humans can use it, that is this arterial, but our animal model, the one that we use at this moment, is a monkey. So we really need to see the cells and really need to see how those are different. And like I finally say, like I really want to see what happened with flow. What happened if we have different stimuli, what happened with the cells. Long story short, we test different, the cells that I showed you before. So the first thing that we do was like, we engineering cells. We know the people here engineered the cells in order that I was able to see them. These are the green, is the nuclei of the cells. And I was able to see in time in my little device what happened in time. So I follow the cells every day to see what happened and if they change with time. And we realized that they align with the flow. But like I tried the human cells, we have changes in the cells. So I moved to the research cells because the monkeys were happening at the same time. And like here is some of the cells, and like you see some alignment with the flow. But like, and we did with Hubex too. This one don't respond that much to flow because if you see they are veins, so they don't do it that much. So, but like we have a lot of variability. So we say, look, okay, is the flow? So I cannot answer that question because I was not sure, because I see variability in all the cells too. So we decide the question can be in our coding, like the way that we are changing the material. And we start to study the material. This has been a long research. So, but like I'm going to try to summarize fast what happened. So we were looking the dopamine, like I say, why we choose the dopamine, and we have really good reasons to choose it because it has an oxidative polymerization that is really easy to do and is durable, and allow me to put another thing that in our case was reconnecting. So we decided to have a chip in order that I can see really well what happened with the cells. We change conditions, we change the dopamine, we change the reconnecting, we try to find it what the temperature, we try to see it what the time. And like we did multiple things in order to be consistent. And we realized that, okay, with reconnecting, I have really nice results. The red thing is the CD31 that is showing me that the arterial cells are still arterial cells that for a while was an issue, but like here is like I have good ones. And like maybe like if I want to put this one in patient, I don't need the dopamine. So now we are able to reproduce the results in the cheats. And the question is like, now we need to see if we can reproduce it in the tubes. We did different studies to see what was the best way, because now I don't have the dopamine to have my reconnecting on top. So how really I can be sure that all the tubes are going to have the material that I want. We tried sonication, but we were opening too much the wall of the material, so we have leaks, and that happened in an animal too. And the other one was like vacuum, and with the vacuum we realized that we were able, like the perfect size to like be sure that the solution was in the wall, but like was keeping the morphology. So we did some studies, and I think that this is the last thing that I'm going to show you. Like we did some studies and the cells look really nice. The cells look happy. We put the physiological waveform all the time for a day. And like that's the thing that we are doing for the monkeys. And like we have monkeys that now are 6 months going and like it's working. But like I said, we want this in patients. So we start to look what happened in a bigger diameter, and the cells are still there and they are looking good. You don't see that much alignment because I have only 1 day of flow. So those are the things that are coming. The coming is like, really, I'm going to start to change flow. That is the variable that I want to study since the beginning. And like, we want to see how the morphology and the gene profile is changing in these cells. So it's a lot of people to say thank you. Here is part of the team is the Thompson Lab, like the previous Thompson Lab, Dr. Thompson, George retired this year. And like the vascular tissue biomechanics that give me the opportunity to start to do these things. And like I have a lot of collaborators helping me to do their designs, to do like the bioreactors, and that's it. So, and I know that the last part of the talk is, so I forgot one. It's like the take home message. It's like research and life is, you always think that it's going to be like a path, like a straight path. And like, I was thinking like the same with my life and with my research. And like, I start to diverse, like go to a different direction. But like, I try to show you here, like little by little, the things start to get together. And I think that is the message. It's like, and with research, it's like, it's not straight, but like with time, you close cycles maybe. So that will be the take home message that I will share with you. And finally, something about me. So, well, I talk a lot about me and why I am here, but like about from where I am. And I decided to say something that I love. And like, I think that all the Latin people really like is like who we are. And like part of who we are is our family. And like part of the thing that I realized with all the life is like from my childhood, my grandparents have like a tradition in December. And they bought tons and tons and tons of corn. And like that, with that corn, so, and then I think about the thing that I'm going to show you, like we are all over the place now. And like with that corn, you put the corn, and like after that, here is in different places in the world, part of the family. The thing that you start to do is like grind the corn for hours and hours, because it's a lot of corn. And like, one of the really nice things here is like, is one of the traditions that bring family together wherever you are. So here is in Arizona, this is in a part of Colombia, this is in another part with COVID and everything. The people go together, do it. This is in the night. Next day at 3 a.m. in the morning, you go start to grind again and again and again. And after that, like more people comes, and like you add sugar cane, you add milk, and it's like similar to manjar or arequipe. You stir and stir and stir for hours and hours and hours. Wherever you are in the world, you stir and stir and stir. And like here, they didn't stir that long, but that was the idea. And finally, you have one of the things that is called natilla. Natilla is a special thing from Colombia, and a special place in Colombia is the coffee zone, where you have this. It's like a pudding, and like the idea is that you do for everyone and you share with everyone during Christmas. And like this is, you eat natilla that is really sweet with buñuelo that is really salty. So that was the tradition that I decided to share with you. And I think with this one, I am ready to open for questions. And again, thank you very much to let me share with you my experience.
Thank you so much, Marcela. Let me stop the recording.